This is our first module of the course. We're going to talk about languages and grammar and give formal definitions for these things. So what we're talking about here are formal languages. Let's start off with that. What's the difference between a formal and an informal, or a formal or a natural? Natural systems arose organically. They evolved over time. There was no committee that decided what should or shouldn't be included in it. They just were created through human usage, and they tend to be highly ambiguous, complex, messy. Formal systems, like math, computer programming, are things that are designed by humans. They were designed specifically to eliminate ambiguity. So the standard example, you go to your bank, how much money's in the bank? They're going to tell you to the penny how much is in there. They won't say, oh, it's about 50 bucks, or it's about 500 bucks. If they did, you'd change banks. So we're talking about well-defined definitions for the elements and well-defined definitions for the operations that you can perform with those elements. And these things form the basis of basically all of computational theory. By the way, there's several bases for that. Okay, so here's the goals for the module. I'm not going to go through them because you can do that on your own. In addition to these PowerPoints, by the way, I'm also supplying a PDF of notes in a more narrative form. It fleshes things out, and also some example problems and solutions to the example problems. Okay, so language definition. Now, because it's a formal system, we're going to take advantage of what all formal systems have in common. All formal systems have a small number of things and a small number of operators to operate on those things. So this is going to be a very small, clean definition. We start off with a symbol. A symbol, a single distinct mark or character. Now we always think of this as something written, and so we start off, usually we're going to use 1 or 0 or A and B and C. In this course we're going to see 1 and 0 or A and B and C a lot. We're going to do that all the time, but any symbol applies. Greek letters, check marks, the scribble you made on your napkin at lunch. Any symbol applies. They have no inherent meaning. This is critical, and this is a hard sell. It is very difficult to get students to pull the meaning away from the definition. So when I talk about language and I ask a student, okay, why don't you give me a definition for language? Oh, it's something we use for communication. No, that's the meaning. The word dog means this particular animal. That's great, that's the meaning. That's the usage of the language. So we want to try to tear apart what the thing is from its usage. And that's very difficult initially. Once you get it, once you have your aha moment, you'll be, oh, of course. And then life gets much easier for you, quite frankly. Your designing of your computer solutions can get much easier. So a single distinct mark or character that has literally no meaning. What about other forms of symbols? Oh, spoken words, other sounds, gestures. Can these be considered symbols also? Absolutely. And one of the reasons that we can accept that is because we can transcribe those and provide a one-to-one correspondence to written symbols. So you've all seen, you've got the happy face emoji, right? Why do we have emojis? We're basically transliterating things that you would see in a conversation in terms of gestures and intonations that people make to a symbol. So basically anything that you can transcribe into a written symbol, you can include in this definition. All right, so we have symbols. What about a collection of symbols? We're going to call that an alphabet. Now, the universal symbol for an alphabet is capital sigma. And it's a finite set of symbols, and typically it's very small. Again, we're going to use alphabets like 0 and 1, or A, B, and C. Oh, wait a minute. What about the English alphabet? There's 26 characters, actually 52, because there's 26 uppercase and 26 lowercase. Yeah, right, there are. But can't you represent those in a computer with 0 and 1? So let's keep our alphabet small. As long as you have 2 elements, you've got everything. 0 and 1. We use set notation a lot. Set notation is the foundation of pretty much everything mathematical. So that's no accident that we're going to use set notation here. The size of a set is always represented using the vertical bars on either side of the set name. So vertical bar, sigma vertical bar, I'm going to read that as the size of sigma. So if sigma is equal to ABC, then the size of sigma is equal to 3. If sigma is equal to 1 and 0, the size of sigma is equal to 2. If sigma has no symbols whatsoever, the size is 0. That's a crazy case, that's a pathological case, but it's important sometimes to make sure all of your systems cover pathological cases. So we know what a symbol is. It's a meaningless mark. We know what an alphabet is, a finite set of symbols. And now a string is a sequence of symbols from some alphabet, from some sigma. Now, again, just like everybody uses capital sigma for the alphabet, we almost always use U and V and W to represent strings. This is just tradition. It's the way the community has grown up talking about these things. So in this course, we're going to use U and V and W to represent strings. Usually if I'm talking about only one string, I'll use U. If I need to talk about 2 of them, I'll talk about U and V. Lambda represents the empty string. That's a string of length 0 and it has no symbols. The length of the string U is represented, again borrowing from set notation. It's vertical bar, name of the string, vertical bar, and I'll usually pronounce that as size of U. So if U is equal to ABBCA, then the size of U, or the length of U, is equal to 5, and the length of lambda, or the size of lambda, is equal to 0 because it's the empty string. Now the empty string is actually going to be important. We're going to use that a lot. For reasons that we don't need to go into now, if you just wanted to talk about all possible strings that could be made from sigma, it's sigma star. Sigma, and then the, what is that mark? Sigma star is how that's called. By the way, when you did set theory in a previous class, probably CS332 and maybe some other math classes, notice what you always talked about. You talked about the set, you talked about the universe of elements that the set could be made from, and you talked about the empty set, the set that had no elements. And look at what we've got here. The universe of strings, all possible strings, is sigma star. The empty string is lambda. And then the set is going to be some strings that we're interested in. All right, so we've got a symbol, meaningless mark, alphabet, finite set of symbols. A string is a sequence of symbols. You know from your previous classes that when we talk about sequence, we're going to be talking about permutations. So now we're set up to define a language. A language is a set of strings. That's it. That's it. Just like the symbols have no inherent meaning, the language has no inherent meaning. When you start to apply meaning to it, you're talking about the usage of the language. The English language is a set of strings that is used to communicate to other people in English. Java is a set of strings that is used to program computers. But that's not what Java, that's not what a language itself is. Right? The language is just the set of strings. So again, I'm urging you to try to tear apart in your mind this notion of what something is and how we use it. It can truly simplify some of the things that you try to design, because you start to get sometimes all caught up in the complications of how something is going to be used. And if you take a step back and say, wait a minute, I just need to design this thing, you know, what it is, and I don't care how it gets used or If I design it right, if I make it right, then it can only be used in certain ways. So you back up to what it is. It can clarify your thoughts sometimes. It's going to be critical to the rest of the course in how we define computation, computability, complexity, language definition, programming language definition, compilation. It's a key thing. And I'm going to urge you several times throughout the course to stop thinking about the usage as the thing and think about the thing. Okay, so that's what a language is. What's a grammar? Well, you know this again. You can borrow from your history in school, right? We all studied grammar somewhere. The grammar, which by the way we'll call capital G, that's pretty universal, supplies the rules by which the language is constructed. So the language is a set of strings, but if the language has certain patterns in it, or if that set of strings have certain patterns in it that you want to bring out, then you can construct a grammar to describe the pattern. In English, the pattern is noun, verb, object, right? That's the basic pattern. Subject, verb, object. Subject being a noun phrase, verb being a verb phrase, object being another noun phrase. That's a standard short form grammar for one form of English sentence. So we assume when we make these grammars that there's a pattern or structure to the language. A set of random strings is still a language, but it's pretty hard to make a grammar for it, unless the grammar just basically enumerates all of the random strings that you included in your language. We're going to use Backus-Naur form. It's basically universally used. Backus-Naur form is one way of specifying grammars. And I'm going to end this talk in a minute and pick up on the second talk, which actually goes into what Backus-Naur form looks like. But basically the Backus-Naur form has production rules. In other words, they're called production rules because they can produce the strings that are in the language. Just like a production company produces a product, the grammar is a production company. It produces strings. And the way that it produces strings is it has two parts, the left-hand side and the right-hand side, which I'll pretty much abbreviate as LHS and RHS. Each side contains symbols. They're connected by an arrow. Some people use a semicolon a colon followed by an equal sign. You'll see both. I like arrows. I'm using arrows. I don't care what you use. And what the grammar rule is telling you, what the production rule is telling you is if you see elements on the left-hand side in a string, you can replace it with those on the right-hand side. It's like a game. There are, it's a substitution game. So if you have a rule, for example, that says capital A, arrow, lowercase a, capital C, A, what that's telling you is if you have a string with a capital A in it, you're allowed to replace that capital A with lowercase a, capital C, lowercase a. So if you have this, I think this highlights here. If you have this here, capital A, in your string, you're allowed to replace it with ACA. So if I had the string lowercase ab, capital A, lowercase ca, since I have a capital A here, I can replace it with ACA. And the resultant string looks like that. AB, notice the AB is the same and the CA is the same, and the only thing that's different is I took the capital A and I replaced it with ACA. Okay, so let's talk about grammars in a little more detail in the next section, the next lecture here.